Let's now see how we can implement the binary search in Java, given that we actually understood very well about how it works at a high level. Let's see precisely the details and also do some tracing. But let me first of all show you how you can find the source code and play with it using debugger breakpoints in Eclipse. And you can go to the project example recursion. It contains all the examples that we're going to talk about in this lecture on recursion. And under the model over here, if you click on recursive methods, and the first one is the binary search together with its recursive helper method. So these are the two methods I'm going to go over with you and also trace them. Under the tests package, open the test case over here. That's a JUnit test case I created for you just to get started. If you click on that, so that's the JUnit test for binary search. I just got some small number of examples over here. You should definitely consider extending them, right? Just to test more and with a larger input. That's something I'll leave to you. All right, that's about binary search, Java source code. Let's now go back. Let's now go over this source code very quickly, but the idea has already been explained, right? So I don't need to repeat too much, but I'll try to show you the correspondence over here, right? So we got some array, input array over here that's assumed to be sorted. It is so important to emphasize this point again. This one over here, that's why I call it sorted. And in this case, we assume that it's sorted in non-descending order, right? So this array should be input array sorted. It's the precondition. And of course, here I'm not really encoding any exception being thrown if the array is not sorted. But if you want to do implement the binary search algorithm yourself, you should actually do it to make sure if any client passes an input array that's not sorted as you expect, in that case, you should really throw some illegal argument exception. I'll leave that part to you. And for the key, it's just any integer, which may or may not actually exist in the array, which you will see different cases of tracing. And we actually got 4 different arguments to another recursive helper method, right? That's based on the basics of recursion. You should really know how to define recursive helper method, right? You should really catch up with the lecture about basic recursion if you have any doubts over here. So we got the input array is simply call by value, meaning that we are not really trying to create any new array along the way. For every recursive call down the level, we simply just pass around the reference to the same array. So it's really making use of call by value as you learned earlier in the advanced OOP course. So call by value over here. That's also very important to note. And I want you to pay attention to these two numbers over here, right? Let me just use maybe here. So you can see 0 and also sorted the length -1. Apparently, this will be the minimum index. This will be the maximum index of the entire array, right? So you can see we got the from and also to. So these are the two arguments and parameters for the recursive helper methods. So what you should know is these two numbers actually define the search space range. Okay, so I'm gonna write it here. So every time we make a recursive call, either we want to go to the left or go to the right half. We have to use the from and to define the range of indices for the search space. This is really important for you to also look at later on when you study the code yourself. So these two numbers define the range of indices of the search space. Right, very important note over here of the search space, right? Of course, it's going to be half, as we said before, each time we try to recur. We want to make a recursion call. Right, so here we're going to talk about some base cases, right? So if you look at from larger than 2, in that case, we simply don't have anything to search, right? So that'll be empty range. That's a base case. In which case, we'll simply return false. In that case, either we haven't. In that case, we simply just haven't found any element yet that's matching the input k over here, right? So that's a base case number 1. And base case number 2 is from is equal to 2. So this will be the search space of size 1, range of 1 elements over there. In that case, all we got to check will be whether or not at a from index, or you can put a to index, that's okay because they are equal to each other. In that case, you can say you can check to see whether or not this element here is really matching the key, right? We're going to see some tracing in a moment, but I just want to explain to you almost line by line. Just make sure you're okay, right? And the else part over here is really the recursive case that we have to worry about, right? Over here. So that's the recursive case. Recursive case. Whereas these two over here are simply the two base cases. Okay, let's talk about a recursive case, and I can use this array to actually show to you. Okay, we have to first of all do some calculation. So the middle over here is simply just the index. So how do we know? So we know that from is over here, and also to is over here. It defines the range of indices of the search space. So in this case, it will be this entire range over here. Later on, from and to may be this particular range, or it could be this particular range, or maybe this range over here, right? It's going to depend on which where we are in the recursion tree, but that's okay. For now, let's say we simply go from the beginning until the end. How do we calculate the middle? We'll simply use this formula over here. The from value plus the to value divided by 2. We'll see exactly what it will be when we trace some concrete example, right? So this will be the middle, will just be the index. And then we got another term over here called the middle value over here. So the middle value is simply just going to be a sorted array index of that, right? So this will be the middle value. I'll say MV. This is middle value, right? So now we're going to compare this input value over here, this key. So the key, let me just use maybe orange. So we got a key over here, and you can see key is also passed to the recursive helper method. So now we're going to compare the key against the middle value, right? So we got different cases, right? You can see we got 3 cases. Case number 1 over here, case number 2 over here, and case number 3 over here. Case number 1 is when the key is strictly less than the middle value. In that case, we know that all the elements that are strictly smaller than middle should be in this particular area. Agree? In that case, we should really recur on this particular sub-range. And how do we specify the range of this particular one, right? Let's say the green area over here. This will be all the values that's less than or equal to the middle value, right? So that's what we're going to do from to middle minus 1. That would make sense because that's exactly over here. You can see we go from over here. From doesn't change, but we're going to narrow the space to only up to middle minus 1. We don't need to check for middle anymore because middle is simply the middle point. And we know that already it's not really equal to the key we're looking for, right? It's middle, I'll just say M, right? Just to save some space. So it's really the middle minus 1 over here. And what about the other case? What if the K is strictly larger than the middle value? In that case, we know that it must be in this particular half, in which case we can disregard this left half. So either we choose the left half to recur, or we choose the right half to recur. Either way, but definitely not both. Right? The idea would be you just keep truncating the search space by half until you reach the 1. Right? All right, let's now take a look at this one here. So this one will be, we basically got this half over here. So what should be its value for the range? So we use middle plus 1 and also 2, right? So that will be this part over here. So we don't need to worry about middle anymore. So that'll be middle plus 1 and also the 2, right? You can see this is the range. If the key we're looking for is strictly larger than the middle value, in that case, it should be over here, if it exists. The final case over here is when it's neither less than nor larger than, then it must be equal to, right? It's kind of implicit over here. So this part over here is really about the else part. Let me write it down. This part over here is really to say the key is exactly equal to the middle value. The key is exactly equal to the middle value. If that's the case, if it's really already matching, there is no point to really go any further to the left or to the right because we know we already found it. In that case, simply return true. Otherwise, we gotta do a little bit more work in the left or in the right. Right? So hopefully it is clear to you how the code is actually supposed to work. We're definitely gonna do some tracing together with you. Let me make a final remark. the binary search algorithm is a recursive algorithm. It's a very typical way of solving problem recursively. Especially, we got two possible occasions to invoke the recursive helper method. You can think about this is recursive scenario number 1 and also recursive scenario number 2. For either this case or this case, you can see we simply try to manipulate the from and also to indices, from and to indices in such a way that the search space over here or the sub-problem we are trying to solve is strictly smaller. That's really the essence about designing any recursive algorithm. You just remember, whenever you want to make a recursive call, you want to make sure that recursive call really is taking some strictly smaller sub-problem to solve. Otherwise, you will just end up in some infinite recursion if you don't reduce the problem size. That's really also covering the basics lecture as well. But I just want to mention that it's so important to keep that in mind. Right? Let me make this final remark, and then we can go on to trace the code. So this over here, either go in this way, or we go in this way. Of course, the fact that one is belongs to if, the other one belongs to else if, makes sure you just cannot go both. Right? So it wouldn't be so clear if you actually say if and also if. I wouldn't recommend it. You want to make it very clear, even syntactically, that you just say either you go in this way, in which case you discard this way, or it simply cannot go this way and you go this way. Right? You want to go for either, but not both. It's more like an exclusive or concept. Right? So for these two, I just want to make a final remark over here. The narrowed search spaces represent a strictly smaller problem to solve. Smaller problem to solve. Right? It's so important to observe this in any recursive algorithm. The narrow search space represents a strictly smaller problem to solve. Right? Strictly is so important. It cannot be the same every time you make a recursive call. Otherwise, you get infinite recursion, which will never terminate. All right, so let's now try to trace this algorithm over here by using maybe two inputs.